Hello all. During the session, during the live session, somehow I couldn't record the first half an hour, so I am again re-recording it. So I will be combine both the that last half of the session and this half of the session, and I'll upload it in the video. Okay. Uh, okay. Hello all. My name is Sriyari. This is the NPTEL problem solving session for course Advances in Welding and Joining Technologies. Uh, the course tutor for this course is Professor Swarupa, um, and myself teaching as actually ADC for the teaching assistant for this course. This is the seventh live session. Today I will be discussing this year's assignment, the course of the sixth week, 10 questions. And actually, I thought of discussing even last year's assignment question also, but somehow I couldn't get there was some login issue, so I will be sticking with only this year's assignment questions. Let me check one second. Yeah, okay. So, uh, uh, in this week, in the welding methodologies thing, sir basically sir started with the explanation of shielding gases under gas metal reactions and slag reactions. In that, he has explained about why shielding gas is important for protecting the molten pool from the weld pool. Apart from that, also shielding gases shielding has also has some other advantages, like in respect to microstructure, and also sometimes bead appear like bead quality, and some like kind of those advantages also we can achieve. So first of all, shielding gases in the sense for any like for any autogenous welding process, for any arc welding process, like if you take autogenous welding, then in that tungsten inert gas welding needs shielding gas, especially the inert gas thing. And also, if you go for deposition welding, whether it is metal inert gas welding or shielded, not shielded, metal inert gas welding, or even we can go for laser welding, even plasma arc welding, there will be a shielding gas. Sometimes in laser welding, that's what. And sometimes even in laser welding also, there will be shielding gases are used. Okay. For let's suppose if I am taking let us in this starting this recap session, I will be mainly discussing how to. As for example, I'll give an example for selecting the uh, shielding gas. Uh, Suppose if we have given a argon and helium uh, shielding gas for TIG welding, means tungsten inert gas welding. Uh, Basically, shielding gases selection of shielding gases uh, mainly based on the metals to be joined. Means what are the metal means what is the metal which you are going to join. That is also an important thing. And also uh, application where you are going to apply. Uh, so application where and also economics point of view also, we based on these mainly these three criteria, we'll select the shielding gas. Application in the sense, uh, suppose if I am some repair works which are not important, some kind of simply joining two metal pieces for some support structure in the household activities or something like that, then selection of shielding is not that important. But if it is in aerospace application or in some if I'm using it for in ship industry or something like that, then the shielding gases is very important. So let us consider. Now, suppose if I have argon and helium are the most commonly used shielding gases for generally in TIG welding process for developing the high quality weldants of reactive, generally of reactive, non-reactive, of reactive and ferrous metals. So first of all, once so if you have a choice to select uh, argon or helium, then we need to look after these factors, which I will be explaining now. So basically, ionization potential of helium is 25 eV, is electron volts, and the argon ionization potential is 16 electron volts. So ionization potential in the sense voltage required to ionize the arc, ionize the arc, ionize the shielding gas. So the ionization potential of helium is higher than the uh, ionization potential for shielding gas is higher than the argon. So this is first point. Then because of the ionization potential is higher, uh, if I use helium as a shielding gas, it results in a higher arc voltage compared to the argon shielding gas because of the higher argon. And also, one more thing we need to consider is the helium has higher thermal conductivity than argon. Hence, so it can be so if obviously if thermal conductivity of a given shielding gas is more than the other shielding gas means effective heat transfer from the arc to the base plate happens. Uh, so helium. So if I use helium shielding gas, then we can uh, use it to increase the use it for higher welding speeds. So that's there. So now once again I'll select it. So helium has higher potential and higher electron potential than the mm, higher ionization potential than the argon, and thermal conductivity of helium is higher. So whenever high welding speed is there, we can go for helium. But due to the higher ionization potential, uh, some problems are faced during the helium shielding gas, like arc instability, and also initiation is difficult. Obviously, if ionization potential is more means like arc initiation is little bit difficult compared to the argon. So so we check the characteristic of shielding gases like ionization potential and also thermal conductivity. Now we will proceed to the next slide. One of the important thing is from the economics point of view is like argon argon's density is around like 1.33 and 10 times heavier than the air and helium respectively. Basically, argon density is more than the air and also more than the helium gas. So during the welding, because the density is more than the suppose if I am using argon as a inert gas, the density is more than the surrounding atmosphere, means air. So the argon gas will be at the particular. So the argon shielding gas will be at the near the weld pool only, and it won't it won't goes away from the weld pool easily because the density of the organ is more. Basically why you are discussing about density is like because it determines the flow rate which needs to be used so that the effective blanket of the shielding gas can be achieved during the welding process, so that we'll achieve good mechanical properties as well as the sound joint. Since helium is lighter than the air, it tends to, since the density is more, it tends to rise up in a turbulent manner way from whirlpool after coming out of the nozzle. So since its density is less, it tries to rise up away from the whirlpool, away from the whirlpool, away from the whirlpool. So this reduces the once it moves away from the whirlpool, we need to supply more helium shielding gas. Uh, so the flow rate required for helium shielding gas is more compared to the compared to the argon shielding gas, because it has a higher density compared to air and as well as helium. So economic point of view, this like shielding gas, like argon shielding gas usage is better compared to the helium, and if fluorate, if the comparatively less fluorate can be used for achieving proper shielding effect, so that uh, prevention of so that prevention of melt pool from the environment can be achieved. Then okay, so we discussed about first point, ionization potential. Then ionization potential we have discussed. Then thermal conductivity. So we'll use it for a higher welding speed. Uh, we'll use it for a higher welding speed. Then because of the higher ionization potential uh, in a helium gas, arc instability and arc initiation is difficult. That is also we discussed. Now density is more in argon, so flow rate is less. So economically, it is cheaper compared to the helium. Argon is cheaper compared to helium. So, so that will see the advantages of argon over helium shielding gas. Uh, so easy arc initiation as we discussed, and lower cost and greater availability, means the lower cost, and also it can be used for, since the thermal conductivity is less, it can be used for shallow penetration required for like thin sheets welding of aluminum, highly reactive metals like aluminum, and since it is a nut gas, you can use it for aluminum reactive metals like aluminum and magnesium alloys. But to avail the advantages of helium also, if we mix the argon plus helium shielding gas, then we can avail the advantages of both, right? Like arc stability will be there, and also arc initiation will be easy if we mix the argon and helium. And also, since helium has good thermal conductivity, then we can achieve higher temperature arc also. So this is how we need to based on the characteristics of the given shielding gas and our application, like where I'm going to apply, means which metals I'm going to use, or which application industry I'm going to use, and economics point of view, based on all these all these requirement along with the characteristics of the shielding gas, we need to select a proper we need to select the shielding gas for our required application. Next, I wanted to little and also after the shielding gases, I don't know why what happened. Some network issue was there. Okay. So, and also I wanted to discuss about the restorations and distortion. As also sir discussed, first initially started with the uh, effect of gas metal reactions and those things. Then he discussed about the restorations, evolution of the restorations in a given weld joint. So before explaining this figure, I will be explaining this figure one. With respect to this, I will explain this how the evaluation of residual stresses in a given component. Uh, this first, especially this figure, I have explained even in second week, and also in something like fifth week. Also, I have given briefly explained about this figure. Anyhow, again, for the sake of continuity, I will be explaining in today's in this class, and then I will explain evaluation of residual stress in a given weld joint. So, first of all, we'll consider a three bar arrangement, uh, which are rigidly fixed like this. Uh, so, uh, initially these three bars are at room temperature. Fine. Now uh, the middle bar, only at the middle bar I will raise the temperature. So middle bar temperature will be raised, and this will be at room temperature itself. So once I raise the temperature, because of thermal expansion, right? Because of thermal expansion, it tries to expand. The middle bar tries to expand. However, uh, it the middle bar try to expand because of thermal expansion. However, the extreme, the like other two bars, like extreme bars, uh, is at room temperature. These three are rigidly fixed. So the other two bars won't allow it to expand. So compressors are generated once it is at heating stage. So now I will stop the heating, and I allow it to cool down, uh, because of the atmospheric convection, and also due to and also due to convection and conduction and other things, heat losses will happen. So once it start cooling, once it start cooling, uh, this middle bar tries to contract. Obvious, right? Like once it is at higher temperature, it expands, and once the temperature decreases for any metal, in general it tries to contract. So the middle bar tries to contract. However, these three bars are rigidly fixed, right? Like these three bars are rigidly fixed, so that uh, the middle bar is about to is getting cooled, there will be a contraction in this, because from higher temperature to lower temperature, contraction happens in general. But since these three bars are rigidly fixed, these bars won't allow it to contract. So it won't allow it to contract. So these bars will, because of these three bar arrangement, there will be tensile resistance in the middle bar, and to balance that, compressor resistance will be generated in the uh, other two bars. So this same analogy can be correlated to the weld joint. Suppose if in this figure C, if I consider this as a welded joint, and this at the center point, initially welding happens, and once I allow it to cool down, the weld metal and the adjacent of the weld metal, there will be a, because of the resistance uh, offered by the base plate, offered by the base plate, there will be tensile resistance at the weld joint, and away from the weld joint, in the farther away from the weld joint in the base plate, to balance the tensile resistance, there will be a compressive stresses, uh, to balance the tensile resistance generated in the weld joint and nearby region. Uh, there will be compressive stresses generated at the farther away from the weld joint in the base plate. So this is how tensile resistance will be evolved in the weld joint. And now, uh, suppose if now I'll explain with respect to temperature in the weld joint with respect to temperature and chill, like resistance graph. Suppose this is a weld joint, and let me take a pen. 1 second. Suppose if I am welding, and the welding direction is like this. So this is the start point, and this is the end point. I am welding in this direction. So, like suppose if I consider section A, it's already welded, and suppose CC also it's already welded, but it is near to the arc. This O represents the center of the arc, means position of the welding arc where it is present. If I consider section BB, currently the welding arc is exactly at this point. If I consider the point like section DD, the welding arc is to be traveled around that, and welding joint needs to be performed. So section DD is not affected. So 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 if I take a welding section DD, uh, it it basically it basically shows the unaffected region means before welding. Before welding, obviously the plates, if a plates will be at room temperature, and there is no construction, contraction and expansion, and there is no any restrictions and those things. So the resources won't be generated. Fine. Now I'll take section BB. This figure, I will put my edit it as. This figure is basically can be represented by figure BB, section BB. So since arc is at the center point, there will be a melted region. There will be a melted region. 1 second, I'll keep charging. So at the section BB, at the center and nearby the arc, there will be a melted zone, and away from the center there will be a mushy zone, and further away from that there will be a like room temperature, not room temperature. There will be a base plate which is in solid. So this farther away from the arc center, this this is a temperature is more. So from room temperature it is raising to superheated state. So it tries to expand this region, basically this region. However, farther away point will not allow it to expand. So there will be a compressive stresses at these regions, and away from that to balance that there will be a tensile stresses that can be shown here. Uh, Initially at the center, since it is a liquid, there is no resistance. In the mushy zone, there will be a compressive stresses. These things basically these accept the center, and away from that there will be to balance that there will be tensile stresses. But once if consider a section C means arc already passed through this section, uh, and it is near to the weld pool, uh, and also I forgot to mention in this the temperature at the center will be suppose if I consider it as point O, means this line means at this point center the temperature from this point to the center the temperature will be rising, right? So like this, suppose if I consider it as x, from x to O the temperature will be rising, like this this temperature diagram, this temperature change is given by this expression. So now if I consider CC section, the temperature at the farther will be like little bit more than the early will be more than the room temperature. But here, obviously, since the arc is paused, the temperature will be more. It's like and again it reduces from this center to this once I move away to the well well away from the weld pool to the towards the uh, base metal. But since it is in the cooling phase, it can be given by the figure and also AA can also be explained with this figure. Okay. So it is in the cooling phase. It tries to contract. It tries to contract, but the further away from the mold weld pool, that the base plate, base metal, won't allow it to cool down. So there will be tensile stresses, and away from that there will be residual compressive stresses. Is followed. In the section A, it is cold to the room temperature. So further development of the tensile stresses and away from the weld pool, there will be a magnitude of the compressive stresses be increased. So this can be explained from this figure. So this is how tensile stresses will be evolved. Uh, so in general, in during welding, there will be a clamping forces. Clamping forces are applied, and welding will take carry out the welding. Once the clampings are removed, because of the removal, there will be a redistribution of the stresses. Due to this redistribution of the stresses, if at any point, if these residual stresses crosses the yield point, then at those point a deformation will happen. That is given, that is called as a distortion. So whenever the magnitude of the tensile stresses is more than the yield point, then deformation will happen. That is called distortion in weld joints. Basically, the definition of residual stress is like locked in stresses in the component once the load is removed. Means once the welding is done, means you can take it as A. Once the welding is done, there is some kind of stresses. So that is called locked in stresses. Once the load is removed. Generally, these are tensile stresses are deteriorate the mechanical properties of the component. So it needs to be avoided. For that, various techniques like short pinning means we can, with the help of short pinning or rolling, we can improve the locally. We can induce locally compressive stresses uh, at these points, so that at the weld over the weld or nearby weld region, so that the locally induced stresses cancels the tensile residual stresses, so that we can improve the mechanical property of the given component. Similarly, even distortion can be avoided by. So this is how the tensile stresses are generated. So next thing, uh, I wanted to discuss little bit about the solute redistribution. Basically, one second, I will explain with the help of pen. Suppose the if I take Suppose if I take as any alloy and I'll use it for any casting or welding, so it will be increased to the more than the super melting point, means at near about the superheated state, and I will allow it to cool down. So how the solute redistribution takes place is a very important aspect. This is mainly influenced by the fluid flow, phase diagram, and also kinetics in the sense phase diagram and many other things. Solute distribution. So now I want, as sir is explained in this class, now I basically in this section I mainly wanted to explain about the how this equilibrium graph is there, and what exactly this actual graph means, signifies and all. So this is basically, this graph is from, suppose if I take any binary alloy like uh, concentration will increase something like this. Here temperature, here concentration, solute concentration and all. Suppose and This region is assumed it as a straight line and explained in this figure. Little bit clumsy is here. Clumsy. Okay. So basically, this linear portion is taken from this point, and it is used for explanation. Suppose my initial composition of the alloy is C naught, and it is uh, when it is ready, when it is cooling down. Once it is getting, this is the liquidous line, this is the solidus line. Once the once it is cooling in the cooling process, once it is reduced, once the when the material is reduced below the liquidus point, the first solid to be formed is given by the concentration Kc naught, where K is the partition coefficient, and in this graph you can see this is the last liquid which is present, and this concentration is given by C naught by K. Means it is more than the C naught. Basically, the solid formed will have a composition of Kc naught. So it will reject the solute. That the solute will be absorbed in the liquid, right? So that concentration is given by C naught K. So this line, basically this point is the solid liquid interface. Basically this point. So if I move like backwards like this till this point, so concentration of the solute will be decreasing, and also temperature is increasing, right? So this is kind of mushy zone. So to explain that, so this region. So initially at the solid liquid interface, concentration will be like C naught by K, and as I go from the solid liquid interface to liquid towards the liquid phase, there will be a mushy zone. mm, where the concentration will be reducing, solute concentration uh, is reducing and temperature is increasing, right? Means from this Ts temperature to it is increasing to TL, and it becomes constant. So from the equilibrium diagram, from suppose if I am considered this as a concentration x and y axis as temperature. X-axis is concentration and y-axis is solute concentration, y-axis is temperature. So from here means liquid interface, solid liquid interface. From here to till liquidus point, the concentration means this is no, it is actually this x is given by the distance from the solid liquid interface. So from as the distance increases, the temperature increases, I can see here, right? But concentration decreases, so temperature increases. This is given by exponential curve, and after the from that point, like in rest of the liquid, obviously it is a initial composition C naught, so temperature will be constant. So this is the equilibrium. But this actual line is given. This actual line is like this is the equilibrium line. But in general, any material won't the material won't follow this actual this equilibrium behavior. So in general, this will be the in actually in welding or in other casting, this will be changed. So that is given by the actual this line actual. And so if I consider, and this actual line and the equilibrium line decides what kind of solidification mode will be achieved. Suppose this actual line is not intersecting with the equilibrium line, then planar solidification will be happening. That generally in laser and all will be laser welding. This kind of scenario can be observed. Laser in like planar and cellular, little interaction is there, means little and super cooling is there. Because of that, we are about to achieve cellular. Similarly, if the difference, if there is a lot, if there is a like difference is more, this difference is more, this difference is more, then there will be a super cooling. So we can achieve column redundancy and equation redundancy. So based on the actual thing and the with respect to the equilibrium behavior, there will be a the there will be different kind of grain structures can be grown, is growing. So based on that, this figure explains the like G is the thermal gradient, R is the growth rate, and G by R. If it is high G by R, there will be a planar, and if it is low G by R, there will be equal in between cellular and columnar end, right? Similarly, GR gives the cooling rate for finer structure. Uh, this like if the G and R is more, then we'll achieve finer grain structure. If G into R is less, then we'll achieve like coarse structure. And this I actually explained in the session, so I'll be merging those videos. I will be uploading. Basically, here there will be solute rejection, right? So the liquid metal will be the lowest liquid. This region will achieve the lowest melting point. Lowest melting point. Uh, Sometimes it is in some scenarios it will be eutectic point where lowest melting point is there. So once these regions construction of these regions starts, there will be transfer resistance. Because of that, there will be cracking. And sometimes like if the difference between the liquid and solid is more, then this kind of scenarios will be more. And also eh, some kind of impurities also gives rise to the hot cracking. Okay, I'll continue the session from now, and rest of the session again I'll record it and again I'll upload. That my system all of a sudden got shut down. Okay, anyway, anyhow, I'll continue the session. I'll start screen sharing. I hope my audio is audible and my screen will be visible now. I think my screen is visible now. Okay, I was here, right? So I was I was explaining that due to the solute rejection from the solid to the liquid, there will be a solute rich in this liquid compared to the solid at the solid liquid interface. So what happens, like how hard cracking is evolved? Okay, uh, due to the high solute rich, due to the rejection of the solute from the like solid to the this region, basically this suppose if I consider a weld pool, because of the the solidification is always in the direction of the higher, in the direction of the temperature like in the direction of the temperature gradient, highest temperature gradient in the opposite direction. So the temperature gradient is increasing like this. So increasing increasing like in this direction, like this. So the growth will be like opposite to that, like this it will be grow. During growing, the it will reject the solid, it will reject the solute, uh, like, and liquid will get more amount of solute, and it have the lowest temperature. Generally, if I take iron carbide iron, it can be like eutectic point, means the lowest melting point. So this will suppose if I consider this is the lowest melting point. So this is already mushy zone, and it will solidify late. But this is since it is a solid, it is getting contraction, right? So because of the contraction, what happens? The, this tensile resistance will be there, so it will drag like this, right, from both sides. drag like this, so we'll have some kind of cracking. So that is called hot cracking. Means it happens during the solidification at the higher temperature. At the higher temperature. So it is called hot cracking. So the definition is like formation of high release zone at the central part of the late solidifying region of the weld. High alloy weld having a long. So if the temperature difference is more means it happens. Means the solidus difference between the solidus and liquidus temperature is more means this happens. So this if the temperature is more means this is very susceptible for the hot cracking. So this is how it is there. Sometimes if I am welding steel, if it is enriched with the sulfur, then this kind of like cracks will be seen easily. And also sir has discussed that. Means sulfur rich will have uh, solidification cracks compared to the magnesium. If the if the alloy has magnesium, then solidification is considerably less. Okay, this is about the hard cracking. Well, one more cracking sir has discussed is one more thing sir has discussed about is like uh, cold cracking. Okay, how this it is also called as hydrogen cracking. Sometimes it is also called as delayed cracking. So let us see how hydrogen cracking or cold cracking is happening during the welding. Basically, mm, much more concepts of welding metallurgy is involved. Just I am giving the brief idea. Suppose how due to the gas slag metal reactions or gas reaction, hydrogen may be resolved, hydrogen may be evolved, and also because of the moisture to the electrode or some kind of dirty atmosphere nearby the weld pool, or some kind of grease is there. So because of arc and all, it it gets evaporated and atomic hydrogen will be formed. Generally, the suppose if I consider the steel, if it is at higher temperature, the steel with higher temperature has having a more solubility of atomic hydrogen. So nearby atomic hydrogen is absorbed by the liquid metal. So so the liquid metal gets the liquid metal in the liquid metal the hydrogen content will be more. Once the hydrogen content is more, so diffusion happens. So obviously the solute the hydrogen thing will be more here. So because of that, a diffusion happens to the nearby solidified metal or heat affected zone. Because the nearby region is also at higher temperature, so it is also higher solubility. So it attracts the means diffusion happens from a higher region to the lower region. So this hydrogen will be diffused to the height affected zone. Once it is done, so cooling happens. Means this arc will move away. This arc will move away and cooling happens. This after this diffusion, what happens if the temperature is decreasing? So, suppose if it is around nearby low temperature, then again this atomic hydrogen is not stable because the solubility will be reducing. The solubility of the metal is less than the liquid metal. So liquid metal absorbs the more liquid metal absorbs the more hydrogen, atomic hydrogen. Once the once the liquid metal or molten pool is solidified, it becomes the it becomes the solid, and also heat affected zone region also reduces to room temperature. So at lower temperature, the solubility of hydrogen is less. So this so this atomic hydrogen is unstable and it tries to move to the lower region. Some like generally grain boundaries. It will tries to move towards the grain boundaries. There, what happens? The atomic hydrogen combines to form a H2 molecules, combines to form a molecular hydrogen. So this hydrogen will be at the grain boundaries, will apply the pressure. Because of the stress will be generated along with the normal tensile stresses. The stresses also will be generated. So, due to the combination of this stress and the normal tensile stresses tensile residual stresses generated during the welding, it will apply the pressure. Because of that, cracking will be happening. That is at the room temperature. So this basically this hydrogen diffusion happens. After that, it like the welding cooling happens, So once the weld joint is cooled, this solubility will decreasing, so it will go towards the grain boundary. So there, hydrogen molecule will form. Along with that, the tensile residual stresses, it will. So it now it is at a room temperature. So uh, along with it, this molecular hydrogen force and pressure, there will be stresses, and also the tensile residual stresses. There will be a hydrogen assisted cold cracking. Since it is cold cracking, because after solidification, the joint is achieving the room temperature, then uh, the cracks are happening more generally at the heat affected zone. Sometimes even at the weld metal. So this is called even delayed cracking. So the main given is cold cracking because it happens after the room temperature. So this is one more cold cracking. So we'll discuss this uh, to like this year's somehow there is some login issue for last year's assignment. So that's why I have given some kind of important recap. Anyhow, before the hard cracking topic again I will discuss because that recorded session is I think not saved. Hmm. So now I will be discussing the so now I will be discussing these topics. Means this year's assignment question problems. So so the question is like following the values of temperature gradient and growth rate are observed in the similar joining of steel and inconel using microplasma welding. Basically, temperature gradient G and growth rate is given. So they asked us to arrange the different welding cases in case of increasing order of cooling rate. So cooling rate in the sense temperature gradient G into R, right? G into R, right? Uh, so uh, so they have given for various cases of welding cases G and R, and they ask us to in the increasing order. So if you multiply G into R for case 1, case 2, case 3, you will be getting the values like 372.3 to 3.26. Here one more thing, this is also given by, since it is not in mm SI units, but it is given in mm, both are given in mm. This mm k mm cancels, so ultimately we'll get like Kelvin per second. So 372.3 into 3.26 will give the this some value, and for corresponding 350 into 3.434 will give the 1190.2 kilo Kelvin per second, and for the case 3 278.7 into 3.03 will give the 844.5. This is the for third case. So if we check these things, for case 3 it is less, then case 2, then case 1. So increasing order is case 3, case 2, case 1. So option will be like 1B. Yeah, case 3, case 2, case 1. So option is 1B. I think it's clear. I am going for next question. Select the possible reason for occurrence of hard cracking in the fusion welding process. Low ductility of the material. Suppose just now when I was explaining, right? If it is brittle means the distances brittle means the cracking will be easy, right? So low ductility of the material, and also if the wide range is there means the central region will get more time, and means it will be at the liquid state at the more um, like mag- for more duration. So due to that, the already solidified metal will be will be applying this tensile residual stresses. Due to that, uh, hard cracking happens. So the 2 is also correct. Presence of impurity elements. Yeah, low melting point like sulfur, phosphorus, and boron. This kind of solutes will again make the central region, means the solute rejected liquid will make the reach lowest melting point. Uh, because of that, the liquid will be at more time, more duration. So solidification cracking happens. But the presence of high level of magnesium, this as sir explained, because of this the solidification is reduced. So the option is 2B. 1 2 3 is correct and 4 is not correct. So they have asked us about the match the type of distillation with uh, table B and type of distillation and highlighted with arrow mark. Okay. Type A and type B I need to match. We need to match. So first of all, longitudinal bending. Suppose suppose this is a welding plate. This is the welding direction. Means this is the suppose this is the welding direction. I think you are able to see my marking and all. So this is the welding direction. So this is the welding direction. So this is obviously the longitudinal direction. I think some issue is there in the internet. Anyhow, okay. So suppose this is the welding direction, then this is the longitudinal direction. Then the other direction, this direction will be like transverse direction. So this is L, this is T. Suppose longitudinal bending means in this direction the bending should be happen. Since this is the longitudinal direction, and if I look into from this side view, I am seeing it in longitudinal direction. There will be bending. So A1 B4 is the answer. Then transverse bending. Transverse bending. Then again, if I look in from this direction, I can see the transverse direction. Transverse direction in the sense this direction. So there will be a bending here. So this is called A like A to B3. A to B3. Then longitudinal shrinkage. Longitudinal shrinkage obviously is given by this thing. This is obviously longitudinal direction. This shrinkage at the longitudinal direction. And A3 B2 and A4 B1 transfer shrinkage means in the direction of this thing. So 3C is the option. And next question given is like for the assertion A and the reason R below the choose the correct alternative. If you guys know the answer, you can please comment it in the chat box. Quenching leads to the residual stress in the specimen, obviously. Because if the cooling rate is more means that temperature difference between the weld pool and away from the weld pool and near the base plate will be more. So residual stress will happen. And the reason they have given is like these stresses are generated due to the different cooling rates at the surface and the center of the specimen. Yeah, this is the obviously correct answer, correct reason. So answer will be like for A, both A and R are true, and R is the correct explanation. This is lever rule. Okay. Basically, for a given binary phase diagram, or if I want to calculate the composition, I think some delay is there in the display. Maybe internet issue. Okay. Anyhow. Okay. For a given copper nickel isomorphous phase diagram, given below, shown below. What have they have given at a given temperature around 1250 degrees Celsius, the alpha phase and liquid phase are present. Liquid phase for a 35% nickel and 65%. So this is the line. Now, if C naught is given as 35%, so and nickel C alpha is given as 42.5%. They have given liquid content as 31.5%. So they ask us to compute fraction Fs and Fl of solid and liquid compositions expressed in weight percentage of nickel. So basically, we need to apply river rule. So if I want to calculate the liquidus phase, if I want to calculate the liquidus phase means if I want to calculate this fraction, so then the shortcut is like in the river rule. I need to do C alpha minus C naught divided by C alpha minus CL. that will gives the like a liquid composition. And also if I want to calculate the solid, so the shortcut is like I need to calculate this difference overall, this difference. So like C naught minus CL divided by C alpha divided minus CL. So as I explained, so if I want to calculate a liquid means this is liquid, right? So we need to go here. Uh, so I need to calculate C alpha minus C naught. This is the shortcut divided by whole C alpha minus CL. So this is they have given as 40, C alpha is given as 42.5 and C naught is given as that's 35%, right? So 35%. Then C alpha minus CL. CL they have given us 31.5. So if I substitute in C alpha minus C naught divided by C alpha minus CL, I will get it as 0.68. Again, so W alpha is given by C naught minus CL divided by C alpha minus CL. Uh, Basically, if I want to calculate this thing, so I need to calculate this point divided this difference divided by this is a lever. This point B is the lever. So if I want to calculate at this point means then I need to calculate near to away from this point means C naught minus CL divided by C alpha C alpha minus CL. So if I substitute the corresponding values, I will get 0.32. So the answer for 5 is A because 0.32 and 0.68. So again, the sixth question they have given statement one is like hard cracking occurs at elevated temperature. Just now I have explained about the hard cracking. During solidification, this hard cracking occurs means at higher temperature. So this is so this is given. So this can be explained as for hard cracking at higher temperature, and cold cracking occurs after the solidification. Means once the metal achieve the room temperature. So cold crack occurs during solidification. This is wrong. So actually it occurs after solidification. Means once the weld joint achieves the room temperature. So the statement one is true, but statement two is false. So the for sixth question, the answer is 6B. I hope I made it clear. If you guys have any doubt, please put it in the chat box. Okay. Okay. Match table A and table B. Here the material and the if I use these gassing shielding gases and table B influence of the gases present. This is actually discussed by in the class by sir. So you guys need to remember it. Basically, and also titanium means if it is allowed to the oxygen, if it is allowed to the atmosphere, it will react with oxygen. So it increases and but ductility will be reduced. So A3, B2, C2, right? For titanium, A3, B2, C2. Yeah. Then aluminum, if the gases like hydrogen is present in the aluminum, then it forms the gas portion, reduces strength and ductility. So for A2, it's B3 and C3. And other option is that for other A1, austenitic stainless steel. Uh, if the nitrogen is present, then it as discussed in this class, it reduces the ferrite and promotes solidification cracking. A1, B1, C1. So I think option for seventh question is C. 7C. Yeah. Then in the next question, evaluate the value of growth rate R for a given aluminum copper alloy in order to have the planar solidification. So they have given like liquidus temperature, solidus temperature, the temperature gradient, and diffusion coefficient. And they asked us to calculate growth rate for planar solidification. So we need to know the planar solidification. Uh, to achieve planar solidification, the condition is like growth rate by G by R, means thermal gradient by growth rate should be greater than delta T by diffusion coefficient dl. Uh, so this is the condition for the planar solidification. Now they are asked us to calculate the growth rate, means R. If I interchange the terms, so R should be less than or equal to dl into g by delta t. dl is given as 3 into 10 power of and here instead of SI units they have given in centimeters. So if you're comfortable, you can directly solve. If you're not comfortable, you can reduce it to SI unit and you can solve. But you can directly solve through given units because everything is given in centimeter. So diffusion coefficient is given as 3 into 10 power minus 5. Then the temperature gradient given as 700 degrees Celsius per centimeter. So 3 into 10 power minus 5 into 700 and, and delta T. Since it is in the, degree Celsius, so anyway it is a difference, so you can directly take like 650 minus 580. It is given as 70. So 70 divided by 700, we will get it as 10. So 10 into 10 power minus 5. So we'll get it into 10 power minus 4. 3 into 10 power minus 4 centimeter per second. Uh, so, uh, so growth rate should be less than or equal to 3 into 10 power minus 4 centimeter per second. So for 8th question, A is the answer. So ninth question, here the question is like identify the correct and incorrect statements related to the occurrence of residual stresses and distortion in welding process. So they have asked like first we'll see the statements. Angular distortion can be minimized by using high energy uh, high energy beam density welding process. Yeah, because because of the high energy beam. Angular distortion can be reduced because my weld pool will be less because of the keyhole and all. The amount of metal deposited is less, so heat input can be decreased compared to the arc welding or other processes. So angular distortion can be minimized by using a high energy beam density welding process. That is true. Then distortion is inevitable. That is true. In any welding process, the distortion is inevitable because of the tensile stresses generated, and also once the clamping is removed, there will be redistribution of the stresses, so that distortion will be evolved. But and they have mentioned like it cannot be controlled, but that is not the case, right? But that is not the case because there are various welding sequences we can follow or other techniques to reduce the distortion. So this is incorrect. Welding residual stresses are caused by differential thermal expansion and contraction of the weld metal and parent material. Just initially in the start of the class, I have discussed about the evaluation of the residual stresses using the 3-bar arrangement. Due to the thermal temperature difference only, the residual stresses are generated. So that statement is correct. So welding residual stresses are caused by differential thermal expansion and contraction of the weld metal and parent material. This is also correct. Uh, and short pinning can be opted as a one of the methods to control the residual stress. Because of the short pinning or other process, we can implement can locally implement the compressive stresses at the compressive stresses. Because of that, short pinning induces the compressive residual stresses, and also rolling also induces the compressive residual stresses. Because of that, residual stresses can be adapted. It can be reduced. So 9B is the answer because the second is the wrong option. And finally, last question. Uh, we need to match the table A and table B. Here it is preheating and post-heating, and the table B, the purpose which we are using. They have given. So basically, preheating is used to reduce the moisture and grease and oil from the surface. Yeah, that is true. This is not the case for post-heating. And preheating to relieve the residual stress, it is not that much affected. But with the help of preheating, you can control the cooling rate. So this is also true. And with the help of preheating, we can reduce the help of preheating, we can reduce the temperature gradient and all. So we can reduce the crack formation and hot, so those things. So B1, B3, B4 is related to preheating. So B1, B3, B4, and post heating. With the post heating also, we can relieve the residual stress, and also we can control the cooling rate. So B to B3, control the cooling rate in the sense after the welding, we can think it in this sense. After the welding, we can modify the grain structure and all those things. Yeah, 10C is the answer. Uh, yeah, I think. Till now, till this point, this session is recorded. And from this till the solute redistribution, this residual stresses, and also the effect of shielding gases, somehow it is not recorded. So I will be again recording those session, and I will be uploading in the Google Drive, and also in the and also in the YouTube. So for I will stop the session now, and again I will re-record it, and again I will upload the video. So I think I will end the session now, and I will again re-record it.